Now we get to calculate the enthalpies of reactions. So the heat associated with a particular chemical reaction is basically what we are talking about when referring to the enthalpy of a reaction. Sometimes this means that upon carrying out a reaction, you're going to generate heat. Other times it means that you will have to put in heat into the reaction for it to happen. So I'm going to show you a quick example right here. We're basically combusting acetylene with dioxygen to generate carbon dioxide and water. That's your typical combustion reaction. And in terms of energy profiles, what this means is that you're going to have reactants at some energy level, shown here on the y-axis. And you're going to have your products also some other energy level in the y-axis. Now going from left to right in this diagram, we're basically depicting reactants going to products. Notice here that there is a little hill that the reactants first need to overcome before they generate products. That's something that will be of importance when you guys reach the next series of chemistry courses. Alright, but for now, basically the difference in energy between the product and the reactant is what we are defining as the enthalpy of a reaction. And this can be determined by various methods because, as we already established, the enthalpy is a path-independent function. It's a state function. So we can use different ways and different methods of determining or calculating its value. One of them is by using heats of formation. The other one is by using something known as Hess's law. And the last one we're going to also look into is the bond association enthalpy. They're not the only ways to do it, and in fact, in future lectures I'll show you for certain processes kind of like a Hess's law type of approach to finding out enthalpies for those particular processes, but we'll get to that in due time. For now, we're going to focus on these three at face value. I want to start with the heats of formation. Now, we already stated that any molecule or element that you may have has a delta H of formation associated with it. And for this reaction, the 2C2H2s plus 5 O2s plus yielding 4 CO2s and 2 waters. The heats of formation are 226.7 for C2H2, 0 for dioxygen, negative 393.5 for CO2, and negative 285.8 for liquid water. Alright, so those are the heats of formation of each individual reactant and each individual product. So what we basically do to find out how much heat this entire reaction generates is to account for the fact that the enthalpy of a product or reactant can be multiplied by the balancing coefficient that it has, and moreover, all of the heat associated with the product molecules can be added together or summed together. The same thing can be done for the heat of all of the reactant molecules that can be added together. And simply stated, the difference between the products and the reactants, in other words, the delta H formation, the sum of the delta H formation of the products minus the sum of the delta H formation of the reactants is what's going to yield the enthalpy of the reaction. So even though the equation here may look kind of ugly, the best way to really depict it is to do the example, right? So we have the equation right here, we have the delta H formation values, so we're going to start with the products. Oh, and by the way, one additional feature is that we need to always divide this by the moles of a reference molecule. Typically, this will be the molecule that you have measured in the lab, like an actual molecule that you have a mass measurement or a volume measurement. But you're going to need to know the moles of one of the gases that you have, right? We cannot dwell with that particular aspect in the last lecture, but in the context of this reaction, you have to divide by the moles or the balancing coefficient of the individual molecule. Now, in examples, I will probably tell you what molecule to base it on, but if I don't tell you that, technically speaking, you're free to choose which balancing coefficient you want to do, but you're going to have to write what moles this is: moles of CO2, moles of O2, moles of C2H2, etc. Right here I'm going to use the moles of C2H2 for the process of getting kilojoules per mole as units. Alright, so here we go. Products. We know that we have CO2 as a product and we have H2O as a product. We are forming 4 CO2s and we're forming 2 H2Os. So what you see right here in the equation is that for the products, we're multiplying the delta H formation of CO2 by 4, its balancing coefficient. We're multiplying the delta H formation of water by 2, which is its balancing coefficient, and then we're adding them together. The same thing is done with the reactants. The delta H formation of C2H2 is multiplied by 2, which is its balancing coefficient, and the delta H formation of O2 is multiplied by 5, which is its balancing coefficient. All of that gets subtracted from the products, and the entire thing is divided by the moles of the reference compound, the reference molecule, which is C2H2 in this example. So we're using 2 since that's the balancing coefficient of C2H2. Alright, so now what we do is we input the values the way they are, including their negative signs. So we have 4 times negative 393.5 for CO2, 2 times negative 285.8 for water, and we're adding those two together since they're the products. We also have 226.7 times 2 for C2H2, and we have 5 times 0 for O2, and we add those two together to get the heat of the reactants. So this is going to simplify to negative 1574 for CO2, negative 571.6 for water. We're going to have 453.4 for C2H2 and 0 for O2. Now notice that we still have to add the products together, we still have to add the reactants together. So we're going to now yield negative 2145.6 for the products, positive 453.4 for the reactants. We're still subtracting reactants for products, so we have negative 2145.6 minus 453.4, which yields negative 2599, excuse me. And that whole thing is divided by the balancing coefficients of the reference compound, which in this case is 2, C2H2s. So when you do that, you're going to find out that the enthalpy of the reaction is negative 1299.5 kilojoules per mole. Alright, so as shown here, we are simply multiplying the delta H formations of the products by their balancing coefficients. We're adding them together. We're doing the same thing with the reactants. We're multiplying the delta H formation of the reactants by their balancing coefficients, and we're adding them together. The resulting value for the reactants is subtracted from the resulting value for the products, and the whole thing is divided by the moles of a reference compound based on the balancing coefficients. Okay? So, in the next video, I'll show you guys how to use Hess's law to find the delta H of reaction.